Good morning, Doctor. We are from Section 6, Group 1. My name is Laiwalin and my group members are Ahmad Danish, Tan Cha Sing, and Yo Kai Jun. Today, we are going to give a presentation on our group project, Combinational Logic Design. First, we will be looking at a problem description on why we designed the logic circuit of the air cooler system. Nowadays, climate change is getting serious, causing the temperature to keep increasing at a surging rate, which will reduce the usage of air conditioner, which usually needs higher power and will release a lot of gases that will affect the climate change. And we replace it with an air cooler which works by cooling fresh air. And this is our block diagram for the air cooler system. In this project, we will be using a combination logic design which represents the different situations that happen to determine whether to switch on air cooler, which is controlled by inputs, humidity level denoted by symbol H, order level O, temperature T, water level W. And when the humidity level is less than 60% of the relative humidity, order level greater than 3 order intensity, temperature higher than 25 degrees Celsius, water level is greater or equal to 1 gallon, the condition of the inputs of the logic circuit will be the logic 1. And the output of this system are air mist humidifier, denoted by symbol M, air freshener F, fan turbine X, and the water pump P. When the output of the logic circuit is 1, this means that output is on.
Hello, I am Ahmad Danish bin Ali. I will continue our presentation. Now this is our two sample that show our input and output data. As one is said, H is humidity level, O is odor level, T is temperature, and the others. From the two sample, we can construct Carnot map, or we can call it as K-map. For explanation, I will take this K-map. As shown, the blue square is presenting T and the green square is presenting O. We can get the basic logic gate and we can convert it to NAND gate. And this is our combination gate. We use interquantous application by our design logic gate for get the waveform. This is our data waveform that we can see our conversion from the logic gate to NAND configuration is correct because both waveform is same. This is how we can read the data from the waveform. H is 0, O is 1, T is 1, W is 1. And the output is M is 0 and the others is 1.
I'm Tan Cha Sing and I'm here to show how to using Intel Quartus Prime software to realize and simulate our project design. Firstly, we need to create a new project. And then in here, we need to choose the Cylon 4GS as our device family, as the Cylon 5 cannot support the timing simulations to simulate our project. And then we just press the finish. And after our project is open, we need to create a new block diagram, implement our basic get schematic diagram in this block diagram. This is our group schematic diagram in Quartus, and here got the 4 input that is HOTW and the 4 output that is the MFXP. And input and output is connected well by using their own basic gate, that is the AND gate, 2 input AND gate, and then 2 input OR gate. And after make sure all the all wiring is connected well, and then we will just press the button that is the start configuration. The Quartus will help us to compute our design, that is the schematic diagram basic, into the language that understand by the machine, that is the Quartus, to proceed to the next step, that is the simulation. The Quartus had done the compilation, and in here we must make sure that our project design, that is the block diagram, has the 0 errors, and this 30 warning can be ignored. And after the compilation is done, we can open the University Program VWF to complete our simulation. And then in here we need to insert all the input and output. This is the timing diagram that contains all the possible input combination, that is start from 0, 0, 0 and end with 1, 1, 1, 1 as sent as the truth table above. And after we have done this combination input, and then we will just start our simulation. But before start, we need to set up and edit a bit from the simulation setting, that is to remove the NOVOPT in the code to make sure that our simulation can done well. After that, we will just start run our functional simulation. Okay, here we get our functional simulation waveform, and then we can see from here. After we done our functional simulation, we can also done our timing simulation. And this is our timing simulation waveform for our basic gate. After we done the functional and timing simulation for our basic gate, we will repeat our same step as the basic gate to also complete our NAND gate to compare each another.
I'm Yo Kai Jun. Now I'm talking about the comparison between the design configuration. There are some difference between basic gate configuration and NAND configuration. The first one is basic gate configuration implement a logical function directly using basic gates like AND, OR, and NOT gate. But NAND configuration implement logical functions using NAND gate only. The second one is basic gate using higher cost, but NAND using lower cost. The third one is basic gate using higher component count, but NAND using lower component count. The last one is basic gate configuration use higher power consumption, but NAND using lower power consumption. The next one is functional simulation waveform. This is for basic gates and this is for NAND configuration. And this part, inputs HOTW are 0, 1, 0, 0. Outputs MXFP are 0, 0, 1, 0. And this result is exactly same with the free flow in the truth table above. And this represents that our logic circuit can function properly. And the next one is the timing simulation waveform. From the both timing simulation waveform, we can see that the time taken for X to start and to end its function is longer compared to the other output. And this is the transition delay time from logic 0 to logic 1 for output M. The delay time here is 7.43 ns, and for logic 1 to 0, the delay time is 7.724 ns. The rest of the output are calculated based on the same procedure for output M, and all the transition delay time are tabulated in table. From table 1 here, it is clear to see that the transition delay time for basic gate configuration is higher than NAND configuration. So, NAND configuration is better than basic gates, which can reduce transition delay time and enhance the performance of logic circuit.